Oh, sorry. Okay. So when we talk about resonant structures are a type of Lewis structures or a type of representation of a molecule. Okay, it's still a two-dimensional representation. We're not getting into the shapes or anything yet, but it's still a representation. Okay, and what a resonant structure is a representation of a molecule that has more than one possible Lewis structure. Okay, so what this means is that these are usually structures that have a double bond, okay, and sometimes that double bond floats around a little bit between the molecule. The electrons kind of jump between those bonds, but there's no adequate description within one Lewis structure to completely describe this molecule. So that's why we have what we call resonant structures. Okay, so it's easier to kind of just see when we do a practice one. So we're going to start with a practice one of ozone. Okay, do you know what ozone is? Yeah. Do you know the chemical formula for ozone? O3. Ozone is O3. All right. So let's start with our Lewis structure for ozone. Okay? Has to have how many electrons? No. How many electrons? How many valence electrons? A lot of you said 3 there. That's scary. Okay. So 6 times 3, which is 18 electrons total. Okay. Our skeleton should look something like this. Right? We're not making any crazy shapes. Nothing like that, right? We're just bonding those together. So when we bond these oxygens, that means we've used up 4, which leaves us with 14. Okay? There's lots of different ways we can get to our next step, but if we start filling on the outside, right, this is 2, 4, 6, 8, 10, 12. That leaves us with 2 electrons left. If we pop those on there, is that complete? No, that's not going to work, right? Because our central atom does not have a complete octet. So that's no good.
Double bond.
Okay, we can double bond. Let's say we double bond this side here. Okay, if we do that, what happens to this oxygen? Got too many electrons, so let's take 1 pair away. So now, if we look at our total electrons, we're supposed to have 18. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so that works, right? But here's the catch. When we draw this Lewis structure, how do we know which oxygen gets the double bond and which doesn't? We don't know. But the truth is, in real life, when we're looking at ozone molecules, you know, maybe half of them are represented by this structure, and the other half might be represented by this structure, right, where the other oxygen carries the double bond. Okay? So we've got 2 possibilities here for how this structure could be represented in real life. So these are what we call resonant structures. Okay? And when we draw a resonant structure, we have to show that these 2 are the same molecule. And we do that with a double-headed arrow. Okay? So we put a double-headed arrow. And truthfully, when we draw a resonant structure, they should really go side by side. Okay? So a true resonant structure for this should look like... and then a double-headed arrow, and then the other molecule. Okay, so that's really what it looks like. We have a double-headed arrow. This is the resonance structure then for ozone. Okay, it's the same thing as what we have down here, except we usually don't draw them one on top of the other. They're side by side. Okay, and they have to be connected with a double-headed arrow. Okay. The reason that we do resonance structures is because there's more than one representation. Resonance structures are most common when we have a double bond or a triple bond or something like that. Okay, most of the time a double bond realistically. And that double bond can kind of flip-flop between these two spots. Okay, there's much more science that goes behind why those electrons move from bond to bond, but we're not going to get into that part of it too much. Okay, so there's a lot more that goes into it, but essentially what you need to understand is that it can bond, a double bond to either of those oxygens. We have to represent both ways. Okay? Now let's try a couple more here. Let me give us an example. Let's try... Let's try nitrite. Let's try nitrite and see what we think. Okay, what is nitrate's chemical formula? NO2 minus 1. Okay, so let's see if this needs resonance structures or if it doesn't. Okay? Nitrite represents how many electrons? 5 plus 12, and then plus 1 or minus 1? Plus 1. Okay, so that gives us 18 total electrons. Okay, our skeleton here. Let me draw it a little smaller. Okay, so we bond. Okay, that leaves us with 14 left. If we fill our oxygens, now we need 2 more. Will that work? No. So that's not going to work. Okay, have you found out that Lewis structures are kind of a guess and check type of a game? Right, so probably don't use pen when we're doing these. Okay, so let's try again. What should be our next solution here?
Double bond.
Probably a double bond. Okay, so we put 2 on nitrogen, right? Nitrogen likes to have 3 bonds, 1 lone pair. Oxygen likes to have 2 bonds, 2 pairs. Let's count these now. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's pretty good, right? So now for our resonance structure, what would be the difference? Same thing, but on the other side. Okay, so this oxygen would be double bonded. Oops. Okay, and there is one last thing that we need to do with a resonance structure. Because this Lewis structure has a charge, because this compound has a charge, we have to finish our resonance structure in brackets. Okay, we put brackets around the whole thing, both together, and we include the charge on the outside of those brackets. Okay, so Lewis structures with a charge must include brackets and the charge on the outside, so you might want to write that part down. Okay, Lewis resonance structures with a charge have to include brackets with the charge, right? And we always do a double-headed arrow between these Lewis structures. All right, questions about resonance structures? You can have more than 2. Right, you can have lots of different resonance structures. 2 is the basic, 3 is pretty common. After that, it gets a little bit more rare, but 2 or 3 resonance structures per compound is pretty normal, okay? Acetate. Okay, and the formula for acetate is C2H3O2, but we see it more commonly written like this, CH3COO minus 1, okay? Why do we think we see it written like this? This gives us a clue as to our Lewis structure skeleton. Okay, this gives us a clue as to our Lewis structure. So hopefully that will help you with the skeleton. Let's try that one on your own. This one will include a resonance structure. Okay, on our acetate should have how many total valence electrons? 24. Okay, when you added just the elements, it gave us just 23. We have an -1 charge, which means we add an electron.
So is that why it's -1?
That's why the charge is -1?
Is that why, like, the compound structure? Okay. I never knew.
And if we look at the distribution of electrons here, right, carbon has, let me show you where the charge sits. We can even see where the extra electron is, okay? So carbon has how many electrons to contribute to the pot here? 4, right? It has 4 valence electrons. And surrounding carbon is 4 valence electrons, right? 1 in each bond, right? One of its own. Surrounding this carbon are the 4 electrons that it donated. Surrounding this oxygen, there are 6 electrons, which it donated to it, right? 1, 2, 3, 4, 5, 6. Surrounding this oxygen are 1, 2, 3, 4, 5, 6, 7. So right down here would be our -1 charge. It'd be sitting on that oxygen. You don't have to know that. You don't have to identify that on your Lewis structures. I just want to show you where that comes from, right? Why some of them have extras, why don't. Okay, so our second structure would look similar. What's the only difference in our second structure? Yeah, we have a double bond to the second oxygen. Okay, and then our brackets goes around the whole thing, and it's a -1 charge. Okay, did everyone remember their brackets? Yes, and remember their charge? And remember their double-headed arrow? All right, good, very good. Okay, any questions on resonance structures? Okay, all right, very good.